Can you believe it? Can you believe it? This day and age, we're taking a look at the software of scikit-learn, also called sklearn, because I think they botched their pip name before. At any rate, it's scikit-learn. You know what it is. It's some Python library for doing lots of scientific computing stuff. It's cool. I've used it. You've used it. If you haven't used it, you should get to that. I think this is old. This is like predating all the LLM stuff. I don't know when it was created. We're only at 1.7.1. If this were Chrome, we'd be on episode like 498 or whatever. Let's see if we can find out when it was developed. 38 days ago is the stable release. 18 years ago is when the initial release was. 2007. I don't know what the biggest hits of 2007 were. Let's look at the Billboard 100. We've got Irreplaceable by Beyonce, Umbrella, Ella Ella by Rihanna. I spent many an evening in the Ugandan dance circuit, hearing that played loudly until 5 a.m. Did I say many a year? I meant many a day, evening. I got that right, I think. Hey, Ash. Welcome. Willkommen. Before He Cheats by Carrie Underwood and some stuff by T-Pain. Okay, so that's what was going on when these people were dreaming up scikit-learn. And we're going to take a look at its source code. This is ants are everywhere. Everywhere, I tell you. Everywhere. Okay. It's going to be too big to really do properly in an hour. In fact, we can probably pull up some sort of documentation. Scikit-learn documentation. And it should tell us about what the algorithms are. Classification, regression, clustering, dimensionality reduction, including things like principal components analysis, model selection, including grid search, which has to be the dumbest of the searches, right? And pre-processing, including feature extraction, which I thought was more or less fancy PCA. This is answer ever sounded like Batman. That's the whole vibe I'm going for these days. Is it's not Batman, but I think in the future it will be. Okay, so we'll pull up there's Kafka from before. If you want to see what that's about, you got to watch the Kafka episode. Pull up new chats and all of these things. Yes, should I have done that before? Yes. Did I do it before? No. Okay, so a lot of this stuff, to me, as I read it, it says linear algebra, linear algebra, linear algebra, linear algebra. K means that this is what, clustering? I don't know really where to start. And by start, I mean we're not going to see all of it. We've done lots of LLM style stuff. I don't know whether to go to something that is LLM adjacent to make it thematically consistent or go to somewhere that the LLMs haven't taken us yet. But check it out. What did I say over here? I said feature extraction sounded like PCA, but then over here, in dimensionality reduction, we have feature selection. What's the difference? I don't know. One's extracting and one is selecting. We'll just go. For whatever reason, I'm feeling let's look at the PCA stuff. That's kind of like basic stuff that we haven't seen yet. I don't know. Maybe clustering is also like kind of basic. They also have data sets. We are going to ignore that. Ensemble, I'm going to assume these are like ensemble. I would love to see me back. Thank you for the donation. I would love to see me in a Batman vibe too. There have been so many Batman movies, though. I don't know what the current vibe is. I'll be honest. We also have neural networks, which I will open it, but I'll probably skip it. Neighbors is probably like K nearest neighbors. Mixture might be cool. And down here in the main folder, we have things that are like more program-y and less statistics-y, like base, exceptions, dummy. Dummy might be dummy variables. Isotonic. I don't know what isotonic means. Iso is the same. Tonic is tone. Isotonic regression, a type of numerical analysis. Okay, sure. I know what monotonic means, but I don't know what isotonic means. Let's look it up in dictionary. They'll give me an etymology somewhere. Of equal tension. Okay, so tonic is tension. I did not know that. Tonos. Very cool. Very, very cool. Okay, so something about a regression where I assume what's going on is that there's some sort of physical analogy where there's like you imagine these having maybe some sort of spring force, and the regression is kind of like the line or region of like equal tension if you have some physical model. Does the word spring appear? No. Does the word tension appear? No. Then let's abandon it. Okay, kernel ridge. Maybe having something to do with like ridge regression or something. And random projection. And naive Bayes. We'll just open a few of these. Conf test. Semi-supervised. SVM should be support vector machines. Tree should be tree stuff. So I don't really know what we want out of this. This was a request from a user whose name is now lost to a different tab. Shive. Here, classical ML library. Known for its incredible documentation. And then there's a, why is this cool? It's classic. We all begin our ML journey from imports to scikit-learn. I don't know if that's still true, but maybe it is. I hope it is. So I was going to do something in the opening folder. Wasn't there like a base? Should I just open it again? Yes. We'll open base just to see what it's about. It's long. So about a little over 1,100 lines of code of actual code. Clone. Construct a new unfitted estimator with the same parameters. So this is just a deep copy of the parameters in the model with no whatever the fields are that contain the like predictions or whatever or data. I guess those are not copied. Just the model itself and its weights or however you want to think about it. We have a base estimator. So it seems like estimator is maybe the fundamental class. The base class for all estimators in scikit-learn. Inheriting from this class provides default implementations of setters and getters, textual and HTML representation displayed in terminals and IDEs, serialization, which is maybe some form of pickling, and data validation. I don't know how they would do that in complete abstraction, and feature names validation. All estimators should specify all the parameters that can be set at the class level in their init as explicit keyword arguments. No star args or star k-wargs. I've never actually pronounced k-wargs out loud, I don't think, except as keyword args. But I think k-wargs or kwargs, let me know how you pronounce it. Ryu is saying, I have not been able to do any real contribution yet, as I get lost whenever I open it. A better way. No, you just gotta pick somewhere to start. Often, if you're looking to do like an open source thing, once you have followed the instructions for building it and playing around with it a little bit, I think the best places are the issues. And seeing if you can, some issues are going to be like debug this super hard problem, Some are going to be like feature requests. You got to kind of search for one that's like easy to understand or easier to sink your teeth into. And I think that's kind of like how you would be onboarded, like at a company or whatever. You would have some sort of project, and issues are kind of the way that you would specify a project, I think, in the open source world. But on good first ones, some repos have good first issues like marked out, but I don't frankly know how good that is as a thing. But Ryu, why don't you tell me what you are interested in? I'll see if I can cook up something for you that might be, kind of like a vector to point in that might be better than where you are now, but will not be your destination, not be like where you're looking to go just yet. But maybe I can be like, head down by the grocery store and take a left, and then ask somebody down there, and they'll get you closer to where you want to be. All right, so this base estimator stuff, this is interesting, at least in the sense that like this tells us what probably the people who made scikit-learn are thinking about. What's the starting point? The starting point is we have this estimator class, and everything is an estimator, and we provide some basic functionality to kind of hook into. We've got some regex stuff. Why? I don't know. This is what representation. So this is going to be like you type your estimator in the Python REPL, and it's going to do some pretty printing. And this is probably regex stuff is probably to find like the parameters of your model. I can't ever remember. I think I have Python here. I like IPython. How about regular Python? What is it called? scikit-learn these days? Yeah. Can I do that? No. I can't do that. I did some ML projects by following YouTube guidelines. Okay, so if you're interested in machine learning stuff, that's hard. Let me think for a second. What's your background, Ryu? Let's ask DeepSeek. Give me some first beginner issues in ML for cutting my teeth on contributing to open source. Doing masters in CS. Got it. Find a project you use or are interested in. Read their contributing guide thoroughly. Set up the development environment. This is not so helpful. I don't know. My gut is saying bug fixes somehow, but I don't know. I think it's going to be a little bit messy. I would just pick. Here's my gut instinct. I wouldn't go for the most biggestest project, like the one that everybody knows about, and I would not go for the smallest project. The biggest project is going to have a lot of people who know a lot about machine learning, putting their eyeballs upon it. The smallest projects are going to be struggling with a lot of stuff that might be too much of a burden for a newcomer. But kind of the middle projects might be places to find bugs where they are solvable, and they just haven't all been solved because of due to a lack of manpower, woman power, human power. So I would kind of go for those. And if you're interested in maybe the algorithm perspective, I would try to find things that are about fixing the sampling or something along those lines, rather than like fixing the API calls to the backend or whatever. But I think you're just going to have to spend time looking at things and struggling, but like kind of like actively struggling, and then like revisit the question after a week or so of doing that. And in a few weeks, I think you'll just have a better sense of what to do. But honestly, off the top of my head, I'm not sure. Okay, so back to the code. Here's whatever classifier mixin is, some sort of mixin for classifiers. And it gives you an estimator type for to classifier through the estimator type tag. The default to accuracy score. So we have scikit-learn metrics accuracy score enforce that fit requires y to be passed through. Enforce that fit requires y to be passed through the requires y tag, which is done by setting the classifier type tag. Okay, I'm not really sure what that's about, but I guess if you have a classifier mixin, then you've got this score function, and everything has it gives everything like a similar API. And similarly with the cluster mixin. Okay, so this is what's in base. Let's see over here if we have any other symbols that are. Can I do like mixin? So we have cluster mixin density outlier. Okay, transformer bi-cluster regression class. Another classifier or no? I guess we already saw. What was the classifier thing we saw here? I'm not sure. I scrolled down too far. Okay, so just different mixins and basically setting up a common API for everything. With that in mind, I guess let's go to covariance. Why not? Methods and algorithms to robustly estimate covariance. They estimate the covariance of features at given sets of points, as well as the precision matrix defined as the inverse of the covariance. Covariance estimation is closely related to the theory of Gaussian graphical models. Is that right? I assume a Gaussian graphical model is you build up a graph and everything has a Gaussian distribution. A graphical lasso is a penalized likelihood estimator for the precision matrix, also called the concentration matrix or inverse covariance matrix, of a multivariate elliptical distribution. Okay, through the use of the L1 penalty, it performs regularization to give a sparse estimate for the precision matrix. Okay, so we've got some sort of L1 penalty. Here, the graphical lasso estimator theta hat is the maximizer of the L1 penalized log likelihood, which is here. And this is the penalty. This is the penalty here. And so on and so forth. Okay. To obtain the estimator in programs, users could use the R package Glasso or scikit-learn. Okay. So this is an area of stats that I don't know much about. This like the mixture models, elliptical. This is what general multivariate normal. Okay, they generalize the multivariate normal, and in a simplified 2- and 3-dimensional case, the joint distribution forms an ellipse and an ellipsoid, respectively, which I think is what you're used to seeing, I think, in Gaussian models. Maybe. Here. Where did that go? Somewhere. There was a GIF that just had an ellipse on it, but I don't know where it was that I was hovering over. Hello, Crystal Core. Welcome, welcome. All right, so covariance. We're going to import the elliptic envelope. And where is that from? I didn't see that. Here. Okay, here it is. So there's some elliptic envelope thing. which is an object for detecting outliers in a Gaussian distributed dataset. So this is, I guess, just has the boundary of the ellipse, and it's detecting things outside of it or something along those lines. Where did my thing go? And we've also got the graphical lasso CV, et cetera, et cetera. And this is just all imports and stuff, which is what I'm used to with init.py, but sometimes people put real stuff in there. Let's look at empirical covariance. We've got log likelihood. Compute the sample mean of the log likelihood under a covariance model. It computes the empirical expected log likelihood, allowing for a universal comparison. Beyond this, software packages and accounts for the normalization terms and scaling. So just normalize so that I guess you're not reliant on the convention of the software packages, which is what I assume this means. Since we are just having a log likelihood of the covariance, it seems. And what are we actually doing? If we look here, we pass in the precision, which is if you are to believe the lies of the man is just the inverse of the covariance matrix. And so we're going to take its shape, which is, I think, the same as dimensions, or like a tuple of dimensions, I assume. It's some matrix. And we're going to whatever emp conv is the ND array of shape, n features, which is the maximum likelihood estimator of the covariance. And this is maybe the precision is not the inverse of the covariance, because you would expect that if they were, these two would be 1 or an estimator of 1. But I don't think that's what's going on, so we'll look that up in a second. At any rate, we multiply them. And we take their sum. N features by n features and n features by n features. So these are both square matrices. So you get a square matrix out. I don't know what sum is doing. Maybe summing the columns or the rows. And we are adding fast log det, maybe fast log determinant, and taking the negative sum. That should be the log likelihood. And then we're subtracting off p times np log 2 and pi. So this has to be a number, whatever it is. And they were dividing by 2.0, and that's the log likelihood. If you're comfortable in Linux, you should stick with that. Windows is so annoying. Oh, sorry, I missed this. One more thing. I'm switching between Windows, Arch, Ubuntu, and Hackintosh. I don't know. Maybe Ubuntu? If you don't know what you're doing, I feel like Ubuntu is vastly easier. Because eventually something is going to break in Arch. Windows, I don't enjoy using, but people do. I don't know. I would personally stick with Ubuntu for now. And also, you can always play around with whatever you want to in VMs and stuff. All right, so let's look up what this precision matrix actually is. Precision matrix. The precision matrix, or concentration matrix, is the matrix inverse of the covariance matrix, or dispersion matrix. In univariate distributions, the precision matrix degenerates into a scalar precision. Okay, so it is the inverse. And what is empconv is like it's like an maximum likelihood estimator of covariance. This is like the precision matrix of the covariance model. So I don't really know what that means. I guess I don't know if that's an estimator. Let's ask the AIs. So I'll say here, answer succinctly what is what's the precision matrix of a covariance model? Is it different from the precision matrix in like general, not of a covariance model? And is it supposed to be an estimator of the inverse of whatever mconv it is? mconv probably. Yeah, you better think. So Ryu, I think a useful principle is to keep things simple. Decide what you're focusing on and keep everything else simple. Yes, here are the answers to your questions. What is the precision matrix? It is the inverse of the covariance matrix, sigma, often denoted by theta or omega. Theta is sigma inverse. The precision matrix of a covariance model is a precision matrix that is estimated or defined by a specified statistical model. The model often imposes certain assumptions or structures like the sparsity in the case of a graphical lasso model. Is it different from the precision matrix? Yes, they can be different. The precision matrix, true. I guess this is like the Greek matrix, the true Platonic matrix, the true unknown precision matrix of the underlying probability distribution that generated the data, and the precision matrix of a model is an estimate or approximation of that true matrix. Your model's precision is an attempt to estimate the true precision matrix. Is it supposed to be an estimator of the inverse of mconv? Yes, precisely. mconv is the empirical covariance matrix, which is your estimate of the true covariance matrix, blah, blah, blah. And mconv inverse is the empirical precision matrix. The precision parameter of your function is a different model-based estimator of that same true precision matrix. The goal of many covariance models is to provide a better conditioned or more interpretable estimate of the precision matrix than simply inverting the empirical covariance matrix. Good. Great. So I wasn't crazy, and I was understanding what's going on, except now I'm confused by this. What does NP sum do? Do I have NumPy? What kind of world do we live in? I have it in my other window here. But let's do returns the sum of matrix elements along a given axis. So it seems like this would be. So what does we have two square matrices. Multiply them. And then NP sum the result. Does that produce a vector of sums of columns or rows or something? Something? It should produce a scalar, because that seems to be what the types are. But the operation produces a single number, a scalar, not a vector. It is a two-step process. In NumPy, the star operator between two arrays of the same shape performs an element. Oh, this is not matrix multiplication. Oh. How do you do matrix multiplication in NumPy? Oh, using the at or matmul. Okay, well, that shows what I know. Draw a NumPy. The Hadamard product. Okay, well, there we go. All right, so this is why? I don't know. So we're just multiplying it by all the elements. This should be, in theory, this should be the identity matrix if you had if this was a perfect estimator, so the sum would be n, the dimension of the number of features. We're taking the number of features, essentially. In general, this is going to be bigger than n, I think. Not in general in the sense that always, but like any deviation from, if you have the identity matrix and you add some like epsilon times the identity matrix or something, or epsilon times like the all one matrix or something, then you would perturb it, and you would have stuff that's not adding to one. Some of it might cancel out. I don't know what the expectation is, but I'm imagining that there's like error, plus or minus some error. But at any rate, we're taking that sum and we're subtracting it from whatever fast log det should be. I assume something like a determinant taking the log and doing it fast. And then we're subtracting off some p, which is, I think, the number of features, because it's shape of 0 of precision. And then we're also taking the log of 2 pi. So we're doing some calculation in log space, which is, I think, why we have pluses and minuses and not multiplications and divisions. And we're dividing by 2. Why divide by 2? I'm not sure. But I guess we can figure all of these out. And NumPy. It's not the worst, but it's not the best. Okay, so back to here. We're not going to spend this much time with all the calculations, but let's do a little bit here. Y. Let's see if we can find fast log det. Compute the logarithm of determinant of a square matrix. So why do we have the logarithm of the determinant of the precision matrix? And why, I forget what we're doing, adding the whatever we're doing. Let's look at the computation again. Where'd it go? Up. Oh, okay. So we're subtracting p times the log 2. Why are we subtracting? Oh, what? Oh, man. I keep forgetting here. What kind of world are we living in? Well, they really don't. The non-pay tier really just doesn't give you anything. Okay. It calculates the sample mean of the log likelihood of the multivariate Gaussian distribution. The terms come from the formula. Okay, so here's the formula. Yeah, I guess that's true. Whenever square root of 2 pi in the Gaussian formula. Mm-hmm. And if you take a log, yeah, okay. It's just from the Gaussian distribution formula, I think. Okay, great. All of that's good. All of it's great. Here's empirical covariance as a function. Compute the maximum likelihood covariance estimator. I could have read this part first. Whether to assume it's centered, and then you have some data, which is the thing that you're using to compute it. You're going to check array, saying ensure 2D is false, ensure all finite is false. And I don't know what check array is, but some sort of like sanity check. And we may do some reshaping, kind of depending on what the shape is. If we assume that we are centered, then the covariance is just using we're dot producting I assume x dot t is the transpose. We're taking the transpose of x with itself and dividing by the essentially the dimensionality. Are we assuming this is square? I don't know if we saw anywhere that it was assumed to be square. Otherwise, the covariance is the transpose, and the bias is set to 1. And we're just calling NP cov, presumably covariance. And if the covariance dot ndim is 0, then I guess we convert it to an array or something. Okay. That's the empirical covariance function. And here's the empirical covariance base estimator. So this is like the class, the maximum likelihood covariance estimator. Read more in the user guide. And this is mainly, I think, going to call out to that function. You can set the covariance, saves the covariance and precision estimates. Here's the fit function, which has a decorator, fit context, prefer, skip, nested validation equals true. So this, I assume this, what did I just call it, a decorator, is there to help guide the API that this is like that this is the function you call to do the estimation or something along those lines. Fit the maximum likelihood covariance estimator to X. And X is an array-like of shape, n samples, and features, so it does not have to be square. Where n samples is the number of samples and n features is the number of features, and we ignore y. It's present for API consistency by convention, which is a little bit weird, but you do. I see why they do that. We're going to validate the data. And if we assume centered, then we'll set location to zeros. The number of, what, features? Which one is first? Features or, I think data is, I think features is first and data is second. Where'd it go? Somewhere. I don't know. I guess it doesn't matter. At any rate. Otherwise, we'll set the location is x.mean at 0. I don't know what the 0 is doing in the mean calculation. I don't think it's just mean of the number 0, because that would just be 0. But there's some parameterized mean calculation, it looks like. And we just call empirical covariance. And then we set the covariance based on what we get, and we return self. And then score, compute the log likelihood of X test under the estimated Gaussian model. The Gaussian model is defined by its mean and covariance matrix, which are represented respectively by self location underscore and self covariance underscore. Samples is number of samples is first, number of features is second. That was the question I had. Okay, and then for the score function, we're going to again validate the data. We're going to compute empirical covariance of something else this time. X test. So we're passing an X test. We're going to score like a test matrix essentially. We're going to normalize its location by subtracting off self location, and then we're going to say assume it's centered. And then we are going to compute this log likelihood of the test covariance matrix we got here with the precision matrix that we have, and so on. And we've got the Mahalanobis. Compute the squared Mahalanobis distance of given observations. So this is like the taxi cab distance, right? We've an array of shape and samples and features. The observation is the Mahalanobis distance of which we compute. Observations are assumed to be drawn from the same distribution. So we get the precision with config context, assume finite equals true. We set the distance to pairwise distances of X self-location, something about new axis with some metrics. So we're calling out this pairwise distances function. I don't know why we need this in the empirical covariance stuff, but somewhere there's going to be this function that computes things. Here, like pairwise in metrics. Okay. Is it bis mehalanibis? Dilip Mahalanibis, an Indian pediatrician. I don't think this is the same guy. Okay, so Bose is another Indian mathematician who's famous for the Bose-Einstein condensate. And here's this guy. Wow. I guess I can't do that. So I'll read about these guys later. And this is the Journal of the Asiatic Society of Bengal in 1936. It was prompted by the problem of identifying the similarity of skulls based on measurements. Uh-oh. That's like some race science stuff. Possibly. I don't know why they were measuring things, but in this year, measuring the similarities of skulls. What's it called? Phrenology? Is this phrenology stuff? Skulls, financial turbulence, and risk management. That person was just going for like the shock value of adding skulls to their paper title. So the covariance matrix seems to be the variance of a multivariable function. So I guess the matrix shows how spread. Yeah. Well, yeah. It's like a generalization of correlation. In probability theory, statistics, covariance is a measure of the joint probability of two random variables. So covariance of xy less than 0. This is the correlation. Covariance of xy is about 0. It doesn't typically look like a circle, but covariance is bigger than 0. This is positive correlation. And then covariance of x with itself should be the covariance matrix. I think if I remember correctly. Let's verify that any of this is true. Maybe correlation is normalized. Because I don't think covariance is bound to be between... Well, here we go. The covariance of x and y is the expectation of x minus its mean times y minus its mean. And it's the expected value of the product of the deviations. Yeah, so I don't think this is bounded between 0 and 1. I think the correlation is maybe normalized. The units of measurement of the covariance matrix of xy are those of x times y. By contrast, correlation coefficients, which depend on the covariance, are a dimensionless measure of linear dependence. In fact, correlation coefficients can simply be understood as a normalized version of covariance. Okay. So that's kind of what covariance is up to. It's non-normalized, and I think this should be, what is it, variance? I think if you compute cov xx, you get the variance, but there might be provisos to that. There might be fiddly bits. var x equals cov xx. Yeah. This was also theorem 29.1. Yeah, so that's what covariance is about. It's like a generalization of like both variance and kind of correlation if you're willing to normalize things to be between 0 and 1. All right, so that's covariance. What else can we peek at? Here's clustering. Again, like I said at the beginning, we're not going to get too much into any of the things. We're just kind of exploring and poking around. DB scan. What is DB here? Density-based spatial clustering of applications with noise. I have no idea what this is, but let's just look at it. I was looking for something like k-means. K-means common. We have pxd, which I think is like a C implementation file. Oh, I see. This is Crystal Core. Okay, we've got C import floating. Okay, so this is some like C, what's it called? Python or some Python C interface stuff with k-means clustering, and we've got the Euclidean dense stuff, Euclidean sparse, average sensors, and so on and so forth, sensor shift. I don't know where the actual C code is. Is that here or somewhere else? I don't know. We've got a Meson file, which should be tell us more. Python is what it's called. I forget what I just called it, but Python gen CPP preprocess. Hierarchical fast.pyx. Is pyx I looked at pxd. That might be the bindings, and maybe pyx is the code. I think that's something like that. Okay, so Euclidean dense. We've got two floating points, A and B. Floating stars, so I guess two vectors. These are both in, maybe that means in parameters. You have some number of features here. B int squared. I don't know what the B is for. And this gives you the Euclidean distance between a dense A and a dense B. We manually unroll the loop for better cache optimization. Okay. So I assume that they are doing this in C because they do it a lot and have figured that this is important to optimize. But this is for what? K-means? K-means clustering. I don't really remember how k-means goes. So you've got some observations. You're going to take the argmin of subtracting off the... Why do we have multiple mu i's? So yeah, you're partitioning it to a bunch of sets to minimize the within cluster sum. Okay, so maybe mu I is like the mean of cluster I. And we're going to have k clusters, which would make sense. So we've got, we're going to find the S that minimizes, X is in the cluster S sub I. And you're going to sum all the things up, and we're going to minimize the distance of the observations from the cluster center, essentially, which it claims is equal to argmin of summing up from 1 to k of the norm of SI, which I assume this is like the size of the cluster times the variance of SI, where mu I, also called the centroid of points in SI, is 1 over the size of SI over X, is the usual L2 norm. Okay, this is equivalent to minimizing the pairwise square deviations of points in the same cluster. Okay, yeah. So this is about the simplest thing you can do. I don't know what the actual algorithm is, but maybe this is a diagram of it. The most common algorithm is an iterative refinement technique. Due to its ubiquity, it is often called the k-means algorithm. It is also referred to as Lloyd's algorithm, particularly in computer science community, and naive k-means, because there exists a much faster alternative. So you've got some initial set of means. Maybe you just pick them at random or something, or just pick a point for each of the means as a guess. We have an assignment step. Assign each observation to the cluster with the nearest mean. That is the least squared Euclidean distance. Okay, so you have some guesses, I guess. You compute the distances from the means. You cluster based on what has the smallest distance. And then the update step, recalculate the means for observations assigned to each cluster. Okay, that's about as obvious. That's about the most obvious thing you can do. Now that I think about it. So you just pick, I'm just going to assume for some of these algorithms, you can think of like trying to optimize your initial guess. I think they're often more intuitive if they're robust to just having like the worst possible guess. So you can just imagine like taking like the first four, if you're doing 4 means clustering, you could just about take the first 4 points or like every fourth point as the centroids. And then you assign based on the distance to that, and then you recalculate the centroids, and you just do it in a loop. Humankind always finds the fanciest names for means. Is that right? Oh, big int. Yeah, I think bint, probably big int would make sense. And this is some picture of the convergence. So maybe they did, I don't know where it starts. How they pick the centroid. I'm guessing the plus signs or the crosses are the centroids. And somehow they just picked them, maybe like they scattered them throughout. And then this is the adjustment process. But you can see there's not like a strong defense of when we get to the end here, when we converge. There's not really a strong defense of why like this point is yellow and that point is blue. These are not super well dispersed, I guess, in that sense. But you can cluster them. And that's the point. Okay. And so basically they do all of that stuff in C. Let's see if we can see the algorithm here. K-means plus plus. Init K and clusters seeds according to K-means plus plus. That must be some other algorithm. In data mining, K-means plus plus is an algorithm for choosing the initial values / centroids for seeds. Okay, I just mentioned that I like to imagine that you choose the worst possible initial values. But that I think that's useful for understanding what's going on, so that you don't fall into the trap of like trying to over optimize that part. But in practice, you don't want to do that because it's inefficient. And this is from 2007. I feel like we've been doing K-means since caveman days. So 2007, we got an improvement. It's an approximation of the NP-hard K-means problem, a way of avoiding the sometimes poor clustering found by standard K-means algorithm. I don't want the background. I just want the cut to the chase. Here, the exact algorithm is as follows. Choose one center uniformly at random among the data points. Okay, so one of the centers is uniformly at random, whereas in my example, I was choosing like all 4 of them. Just use 4. For each data point, X, not chosen yet. Compute D of X, the distance between X and the nearest center that has already been chosen. Okay, that seems like a good and simple to compute thing. Choose one new data point at random as a new center using the weighted probability distribution, where a point X is chosen with probability proportional to dx squared. This ensures that a very dissimilar point to the previous selected centroid is selected as the next centroid. Okay. So d of x is a function. So I think what this is saying is it's you want the so for each data point you essentially have a table. Let's call it a vector of the distances to the nearest center. Currently, we just have one. And then you scale everything essentially by dx, by this table squared. Or you turn it into a probability distribution, presumably via scaling. Although you probably don't actually have to have it be a distribution to do the choice. But anyway, you do it, and use to choose one as a new center. But does the data point have to be the center? I mean, does the center have to be an existing data point? I don't know. And then you repeat this until the k-centers have been chosen. Now that the initial centers have been chosen, proceed using standard k-means clustering. Okay. All right, so you can do that. And that's reasonable. And we should see, this should be the code to do it somehow. We're going to check the array, check the X shape, etc. Check the random state, whatever that means. And then we're just going to call underscore k-means plus plus. And here's the computational component for initialization of n clusters by k-means plus plus. And it assumes prior validation of the data. So you'll notice that a lot of the work they're doing is like, you might call it type checking, except that if you had a proper type for all of this stuff, like the type is kind of like the data exists, has some shape. It's not like infinite data, all of that sort of stuff. The pattern in scikit-learn's code base is to kind of check all of that stuff kind of in the main function and then hand off to like implementation functions, such as with an underscore. Okay. So the first one will be random. And whatever this is sparse stuff is, we'll ignore that. And then initialization of the closest distances and calculate current potential. So we're going to calculate the Euclidean distances, which I think is maybe the C code that we saw before. Passing in the centers at 0. Right now there's only one center, I think, if I understand the situation correctly. And whatever NP new axis is. But also x, which I assume is our data, and whatever y norm squared is. X squared norms. Squared is equal to true. So this is the dx stuff from before in that Wikipedia article, which I think is closed now. I think this is essentially saying that we are, that maybe this is the distance sort of that we're calculating, or maybe this is an out parameter. Has x squared norms appeared yet? Not that I really see. And then we get a current pot is the closest distance squared at the sample weight. I'm not really sure what this is doing. I don't remember what at does in Python. And at any rate, we're going to pick the remaining cluster n clusters minus 1 points. So we're going to iterate over the n clusters. Maybe pot is potential. We're going to take a uniform sample, multiply by the current potential. That's going to give us random values. Choose center candidates by sampling with probability proportional to the square distance of the closest existing centers. Yeah. And then we're going to call NP search sorted with a cumulative sum of sample weight times closest distance squared, passing in the random values. So somehow this is going to do the search, and that's going to give us the candidate IDs. Whatever XXX is, numerical imprecision can result in a candidate ID out of range. So this is some clipping. And then we're computing distances to centers, etc., and so on and so forth. And then we're adding best candidates. Okay. So that is some k-means stuff. We saw the handoff to C. We saw k-means plus plus. DB scan is some density-based clustering scan. I don't know. Optics. Let's look at optics. Ordering points to identify the clustering structure optics. This is not about the science, the physics of optics. This is about some clustering thing called optics. I feel that this was clickbait, whoever invented this name, so I'm not going to look at it. Ensemble, we have gradient boosting and bagging. Should we look at bagging? All right, I've been doing a lot of 2-hour streams, so I'm going to try to keep this closer to an hour. The good old days of JavaScript. Oh no. It would be cool to, I've often thought, not often, I've occasionally thought that it would be cool to have like a well-typed math or data science library, but then I think maybe that would not be cool. Maybe that would not be cool. Maybe that's too much overhead. But, you know, it's hard to debug. It's hard to debug programs where everything is like a vector of like floats essentially, and that's where we are in in AI these days in numerical Python. So bagging should be some way of having classifiers. I don't know if it's just tree-based classifiers, but I think the idea is you have multiple classifiers and they are all a little bit not great. And by combining them, you have a better one that's cheaper to train. But I'm not positive. Let's look up on bagging. Maybe bagging scikit-learn. Just so we don't get... I think there might be multiple definitions of bagging. Let's see what scikit-learn says about it. A bagging classifier. A bagging classifier is an ensemble meta-estimator that fits base classes each on random subsets of the original dataset. Base classifiers each. I think a meta-estimator is a fancier way of saying what I'm saying, and base classifiers with an S means multiple of them. Each means multiple. So I think this is consistent with what I'm saying, that you have some weaker classifiers essentially on random subsets of the original data set, and then aggregate their individual predictions either by voting or by averaging. I would consider averaging a form of voting to form a final prediction. Such a meta-estimator can typically be used as a way to reduce the variance of a black box estimator, for example, a decision tree, by introducing randomization into its construction procedure and then making an ensemble out of it. This algorithm encompasses several works from the literature. When random subsets of the dataset are drawn as random subsets of the samples, then this algorithm is known as pasting. If samples are drawn with replacement, then the algorithm is known as bagging. When random subsets of the dataset are drawn as random subsets of the features, then the method is known as random subspaces. Finally, when base estimators are built on subsets of both samples and features, the method is known as random patches. Finally, when a poodle's eating noodles, and the noodle's in a bottle, and the bottle's on a... How does it go? I don't remember. When beetle battles beetle, in a puddle in a bottle, and the bottle's on a poodle, and the poodle's eating noodles, that's called a tweedle beetle, poodle puddle, paddle battle. If I remember correctly. Okay. Who? Let me ask you. Who classifies the classifiers? You know? Who classifies the classifiers? All right, we're not looking at neural networks. We're not even looking at neighbors or model selection. We're going to get rid of all this stuff. I have to look at naive Bayes. It's just who I am. But after, we'll do the bagging, and then we'll do naive Bayes, and that'll be about it. Oh, that was bagging. No. There we go. Okay, so we're gonna select random stuff, and based on the documentation we just saw, there's going to be like fiddly bits being like, how do we select the random subset, etc. But we're going to create some sort of, not quite partition, because a partition implies that there's no overlap, but we're going to sample the data set in some ways according to some whether we're sampling the features or we're sampling the data itself. And then we're going to have classifiers, and then we're going to vote on them. And the sampling part is maybe not so interesting. Maybe the voting part is most interesting. Generate bagging indices. Randomly draw features and sample indices. This is just going to be _ generate indices, passing in random state, bootstrap features, and features, max features, sample weight is none. Normalized sample weight is sample weight over the NP sum of the sample weight. Okay. Consume sample weight, parallel build estimators. I'm guessing parallel means parallelize across CPUs. For I in range number of estimators, we've got seeds. We're going to call ensemble make estimator Append is false. Random state is being set. And then we're going to call down here, draw a random feature, sample indices using normalized sample weight as probabilities if provided. That's going to give us features and indices. I thought up here, I guess make estimator doesn't mean train the estimator. I thought this was doing the training, but it's not, because down here we're doing this, generating the bag indices here. And here we see this note. Row sampling can be achieved either through setting the sample weight or by indexing. By setting, okay, the former is more memory efficient, therefore use this method if possible. Otherwise, use indexing. Okay. And then we're going to append the estimator that we made in this for loop to the list of estimators. And we're going to append the estimator's features. And we're going to return this pair. But where's the parallel here? I don't see... Hi. Hello, MD explains. I don't see how this was done in parallel. Oh, here we go. Wait, what? Is this the same function? This looks like fit. Fit is where I want to be anyway, so let's go there. All right, here's base bagging. This class should not be used directly. Use derived classes instead. Okay, fit. Build a bagging ensemble of estimators from the training set. Yeah. Validate data, sample weight, blah, 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 self.fit. Here's self._fit rather, and here's self._fit. And I think that this is maybe where the parallelization happens. Parallel loop. N jobs and estimators starts is equal to underscore partition estimators. And then all results is equal to capital P parallel of passing in jobs, verbosity, and parallel args. Whatever a delayed is, parallel build estimators, and estimators, etc., for I and range n jobs. I don't know what capital P parallel is. This must be some library. I just want to know how they do it, because Python doesn't like to be very parallel. Maybe it does more these days, but you know, they have that whole interpreter lock thing. Where'd it go? Here. Okay, this is just some library that they've cooked up. Presumably is a abstraction layer over some other library that dispatches threads and stuff. Can I see the source code, man? Thread pool. Thread pool control. Maybe that's the library. joblib/thread pool control. Python helpers to limit the something something. To limit the number of threads used in thread pool backed of common native libraries used in scientific computing and data science. What? Okay, so somehow they're doing... I don't really have the... I wasn't expecting to go into anything this complicated. I just wanted to see what library they were using. Iterable, config with config, blah, blah, delayed func. Yeah, okay. But it seems like maybe they're using this library. I don't know if there's also joblib. Is joblib like a parallel thing? Running Python functions as pipeline jobs. Okay, that might also be parallel. Yeah. Okay, so they're using some combination, I think, of joblib and whatever that thread pool control stuff was. And colony optimization. Oh, is that in here? If so, we'll find it. Have I ever heard of Feynman ants? I have not heard of them in connection to Richard Feynman. Well, he and I have something in common then. I'll have to. Some ants came out around the bathtub, and I thought, this is a great opportunity. I put some sugar on the other end of the bathtub and sat there the whole afternoon until an ant finally found the sugar. It's only a question of patience. The moment the ant found the sugar, I picked up a colored pencil I had ready. I had previously done experiments indicating that ants don't give a damn about pencil marks. Language, Mr. Feynman. He walked right over them, so I knew I wasn't disturbing anything. And he's going to draw lines. I'll read this later. This is cool. I wonder how these fancy... I'm not... I'm not digging into the fancy thread pull stuff now. Non-toxic ant fairy. Okay, so there is ant colony optimization. It is cool. I don't know. I don't know if it's related to the Feynman stuff. But all of this is cool. I have not heard of this. Everyone should look at this. Okay. But now I do want to look to see if there are ants in scikit-learn. What I really wanted to do here, though, is check for voting. So let's check for ants. Ant colony. There's also stuff like Sugarscape. So where is ant colony optimization? I don't know. So Sugarscape is like a you can do kind of like an ant colony. What's it called? Agent-based model. I don't think we've looked at an agent-based modeling framework yet, although maybe we have. I feel like we have. Okay, so I want to know about voting. Resort to voting. Estimate or predict X features, predict proba params or empty dict. For I and rage, proba I predictions I plus equals 1. What? Parallel predict proba. Private function used to compute the proba predictions within a job. I don't know what proba is. I'm not sure. Like I said, I want to keep this short, so I'm not going to dig in. I thought voting would be something that would is proba a thing? Attempt? Is it just short for probability? Predict proba or the proba method. Parameters routed to the predict log proba, the predict proba or proba method of the subestimator via the metadata routing API. The routing is tried in the mentioned order, depending on whether this method is available on the subestimator. And proba is short for probabilities. So this is some prediction. So okay, so this is just calculating the predictions, and then we're just iterating over them and incrementing them all by 1. I think. Maybe this means resort to majority voting or something. It seems to have an impoverished idea of what voting is. But what are the other options? So if you're not doing voting, then what are you doing? Like averaging? So if it has the attribute predict proba, then the proba estimator is the estimator.predict proba of whatever x, passing in something about the features, or like slicing in the features and getting the probability prediction dictionary, or if it's not there, setting it to the empty dictionary. And then we're going to look at the length of the number of classes in the estimator. Maybe, I don't know if classes underscores the number of sub-estimators, or if it's, I would guess that if we're doing like a classifier, that this is the number of classes that we are classifying into. At any rate, we get n classes. And we set proba plus equals the proba estimator. And then otherwise, we don't have n classes equal to the estimator dot classes underscore. In which case, we're going to set the probas to the proba estimator, passing in from the 0 to the number of classes. This seems somewhat opaque. I assume that what they're doing is something like computing the mean of the estimates, but they're just doing it in like some sort of something involving these dictionaries. I don't know really how they are populated or what any of these things are. And it's not especially readable, so I'm just moving along. Okay. And I'm going to just do a quick look at naive Bayes. Naive Bayes algorithms. These are supervised learning methods based on applying Bayes' theorem with strong, naive feature independence assumptions. Okay. So Bayes' theorem, assuming the features are independent, is that the idea? Base NB. Compute the unnormalized posterior log probability of X. That is log PC plus log of P of X given C for all rows of X, all rows little x of big X, as an array like of shape and samples and classes. And then we have public methods: predict proba, predict log proba, and predict joint log proba. Pass the function through underscore check X before handling, etc. Okay. So what does predict do? We're going to check. We're going to get the joint log likelihood of X, and that's going to be JLL, joint log likelihood. We're going to return self classes underscore of getting the argmax of the log likelihood along axis 1, which is the classification prediction. That makes sense. We get the log likelihood, and then we make the prediction according to the class with the highest likelihood, essentially. And if we do predict log proba, this should, I think the idea that maybe predict, it's going to predict one classification, and log proba is going to maybe give you the probabilities of all of the classes or something along those lines. It returns an array-like shape and samples and classes, returns the log probability of the samples for each class in the model. So maybe, I was wrong. So predict doesn't just return the most probable classification. It returns something of shape and samples, the predicted target values for X. One for each sample. Okay, so I guess you're not just classifying one thing at a time. You're maybe classifying a whole bunch of stuff, and it's giving you the classification for each like row or whatever. And here you're getting something of okay. So this is what I'm thinking of. This is what I was thinking of, but there's like there's extra dimensionality to the input than I was thinking. So here you're basically getting back the full probabilities instead of just the class for each of the rows. And so what are we doing? We're getting the joint log likelihood like before. We're going to normalize by P of X. which is the P of F1 to Fn. I assume feature 1 to feature n. We're going to take the log sum exponential of the joint log likelihood along axis 1. That gives us log prob. Because the likelihood doesn't have to be a probability function. And then whatever np at least 2d is of log prob x transpose. Subtracting that off the joint log likelihood. Why this part? I'm not sure. This is just giving us the sum. This is, I guess, doing the rest of the normalization. And that's basically giving us the probability, which is essentially more or less the log likelihood, except with normalize. So it's probability 0 to 1. You know what probabilities are. And then that was what? Predict log proba. Here's predict regular proba. We're just going to take the exponential of predict log proba. That's simple. Here's a Gaussian NB. Can perform online updates to model parameters via meth partial fit. Okay, I think that's about it for me. We've explored scikit-learn. We've learned a little bit about how it works. We've seen some statistic stuff, like k-means. What else did we do? We learned about ants and Feynman's ants, and that's about it. So, thank you for exploring scikit-learn with me. There's just so much there. We could probably do like a full week on scikit-learn if we were truly motivated. I'm not sure I feel that motivated, but there's a bunch there for you to explore if you're interested in Python and numerical data science, machine learning, statistics, any of that stuff. It's a cool package. It's a great package, and you should play around with it. And that's all for me. I'll see you guys next week on Ants Are Everywhere.